Please welcome to the stage Manager of Industry Partnerships and Outreach at Argonne National Laboratory, David Martin.
All right, welcome to the next session in our invited talk series. So we're really pleased to have two representatives of industry here, a large company, Ford, and then a smaller innovative company, T Technologies. So we are going to start with Ford. I'll introduce Dave Kepczynski. Dave is the Global Chief of Digital Transformation for Product Development at Ford Motor Company. Prior to Ford, David spent 10 years with General Electric, most recently as the Divisional Chief Information Officer for Corporate Digital Technologies and Research, where his team developed and scaled advanced computing, digital technologies for business and healthcare, energy, and aerospace. Before GE, he spent more than 20 years with General Motors, leading teams in global digital engineering system, product development, operations, and manufacturing engineering. Most importantly, he co-chaired the U.S. Department of Energy's Exascale Computing Project, Industry and Agency Council, and chaired the American Institute of Aeronautics and Astronautics Digital Engineering Integration Committee. And David is also an advisor on Hewlett-Packard's Enterprise Technology Board. So join me in welcoming Dave. Yeah.
Appreciate it.
Yep.
I think we can move to the next slide. Hello, everyone. Let's go one more. No, there isn't. I think I'm relying on them.
Oh, really?
Yep. If we could advance this, there we go. So just to give a little background on the company, Ford has been in the automotive business since 1908, starting with the Model T. I think many people know the history. But today, we're going through a very large digital transformation in the company. Really not only focusing on vehicles, but really working on electrification, software technologies, and then amplifying that into software-enabled products and services. Ford today is actually split up into multiple divisions. We have Ford Blue, which represents not just the legacy, but a lot of the internal combustion engine and eco and hybrid vehicles. The Model E portion, which is really focused on electrification. Ford Pro, which is actually working on heavy-duty applications and services, and Ford Credit. If you want a vehicle, we help you out from a Ford Credit line. There's three areas I wanted to focus on today to let you know where we highly leverage high-performance computing. We have over 2,000 computer-aided engineers that are doing modeling and simulation every day, and we do have a large computational environment that everyone leverages. But the three areas I'm going to talk about are around safety, performance, and the third piece is around connect, which has really come on significantly over the last years. But first, around safety, the areas of the vehicle that all of us rely on in thinking of our future purchases of a vehicle have really changed over the last decades. There are the traditional pieces around structures and closures and the hardware components, but today there's other pieces coming together around the interior and software technologies and the pieces that are the safety components that we rely on for crashworthiness. We're also looking at the occupants in the vehicle. I think everybody used to think of them as just the crash dummies, but today we're virtualizing all of that and we're thinking of everything as a system. So what's really transformed is we're taking the data, the models, and we're leveraging everything at a system level with compute to be able to understand how all of that's coming together. And what that's doing for us is we're looking at all of the other interactions that are coming together to help leverage the best solutions going forward. So our modeling and simulation isn't just about one thing anymore. It's really about all of the things coming together. And you'll find that to be a theme in each of the next couple of categories that I'll be talking about as well. Performance. The other piece that we rely on is we want the most fuel-efficient vehicle. And one of the key pieces is the aerodynamics of the vehicle. But once again, it's not just one piece coming together that the engineers are working on. They're really working on the aerodynamics combined with the propulsion system, combined with making sure that it's the best riding and handling and sounding from a noise, vibration, and harshness. And once again, working on all of the first principle physics, but not only at component levels anymore, at system levels. We're looking at all the interactions coming together. And just like we're doing full vehicle crash simulation, today we're able to do things in our computational environments that are beyond just component or even subsystem levels. We're really looking at the systems. And once again, the common theme that we're bringing together is around the data, the models, and the compute. And in this area, once again, is how we're highly leveraging our high-performance computing. The third piece may be newer to some of you, but not to us. Vehicles have been an operating IoT, I know we use the term Internet of Things platform, for years, even decades. We've been sensory enabling and connecting vehicles for a long time. But now what we're doing is we're taking that data, and on top of it, we're able to introduce analytics, and we're able to look at what's happening real time with the vehicle. So the sensors are now connected to the control systems. We have telecom that gives us the ability to actually access and be able to know at any point in time, real time, what's happening with the vehicle. And then on top of that, we're beginning to apply applications and services for everyone. Once again, rolling everything together at a systems level. And maybe a little bit different in terms of the computing that we're doing here. You know, in the other areas, we're really focusing on systems, first principle physics, mechanical and structural and fluid dynamics, all of the things that we know here at this conference that many people work on. But in this area, it's really around applying data and analytics, and even machine learning and AI. This is an area where our computational systems are not just the CPU or heterogeneous GPU systems. They're mostly GPU systems, because that's where we're doing the large-scale data and analytics. And once again, the common theme is around data, models, and compute. Before I get to the slide around outcomes, I do want to recognize, because we're here at the Supercomputing Conference, and we're all, whether today is one of your first or second trips here, or some of you have been coming here for years or decades, I do want to recognize an inflection point that's happening right now in supercomputing. We're actually in a new era of computing, where things are multiplying not the typical 2x, 5x, or 10x. We're actually getting multipliers of 100x or 1000x. And these are true statements. We've seen this in our industrial applications of applying heterogeneous systems. We're seeing this with our US government national laboratory partners, where they were really the first to introduce the largest scale exascale systems here just recently. And by the way, at this conference, even the latest information has come out, and there's been a re-rack of the top 500 list. The latest is that at Lawrence Livermore, El Capitan has now taken the first spot in the top 500 list. We have Oak Ridge National Lab with Frontier still in number 2. And even as we have Argonne National Lab still coming online, solidly at 3, but even the ability to move around in the top 3 spots. And then I'd be remiss if I didn't say what's happening out at Los Alamos with the latest NVIDIA machine with Venado. And I'm saying these because I'm hoping that everybody is becoming familiar with just what's recently happened here, because over the last decade, these have been kind of in the pipeline and are now coming out and coming online at scale. They started off as the US government's Department of Energy and Office of Science and Technology Exascale Computing Initiative around the hardware, and the Exascale Computing Project, which was working on the applications, the software, and the integrations, so that as the hardware came online, we were not thinking of what we wanted to do. We were ready in many areas to already leverage these amazing machines. So my piece here is I wanted to tie what's been happening with what we're doing in industry. And we had this opportunity, a number of industry partners together as part of the council. But it wasn't just for us, it was for all of industry, to understand what's happening with these technologies as they're rolling out, how can they be leveraged, what can we do in advance to prepare for it, and I wanted to leave everybody here with some key areas and key thoughts, some of which you already know, and I've heard this before. Well, a couple of these pieces, you're not telling me something novel, but there are many times when I dig a little bit deeper and I ask the questions, and I've done that even at my own company now that I'm at Ford, is we start to learn that while people know them, it's the learn and deliver piece. It's apply them. Find areas where we can take this great knowledge that we've learned, and it's the latest technologies, and begin applying them. So the first three are around systems. I mentioned this before around the exascale computing project. There are some key technologies and capabilities that came out. There were people and process that also came out. The first is around a systems approach. Like I mentioned earlier with what automotive and aerospace has been doing, and thinking of data, models, and compute, and more of a systems approach, the exascale computing project and initiative actually did the same thing. They looked at not only the hardware, they looked at the software, and they looked at the integrations, and they used the term co-design, but they were already working on it in advance of the new technologies rolling out. It's a very important piece. And with whatever you're thinking about, whether you're in academia at a university, whether you're at one of the national labs, whether you're in industry, think of that. Think of the systems approach, and think of the integrated parts of bringing everything together. The second piece is around GPU acceleration. And I think everybody's been following this story for many years, especially in engineering and the scientific community. You know, GPUs are great for visualization. Dave mentioned earlier I worked in automotive years back, and I'm back in automotive again. But once we got to programmable GPUs, things really did change. And there were some realizations on what we could do with today's software, refactored, and highly leverage the parallelization in programmable GPUs. And that's really coming to light. So that's why I use the term here, the new and the modernizing. Some of it truly is creating new software that is an approach, but even what we have today, and it's been proven with our other partners in many of these areas, that modernizing what you have in terms of refactoring can also take advantage of GPU acceleration. And this has been a big piece for us. When I use the numbers there, 100x or 1000x, they have surpassed just what we would normally expect in the hardware technologies coming out. We're really doing it with a combination of the hardware, software, and applications being co-designed, refactored, and being able to leverage that in a different way. The next piece is around machine learning and AI. And I get a lot of questions on this. You know, is it hype? Are we actually creating things? Are we practically applying? And I would say it's a combination of those, but more so on the we are creating things and we're practically applying. I'm seeing that everywhere. And in the early pieces around safety and performance and connected vehicle, we're already applying and creating novel products around practical applications of machine learning and AI in areas of generative design, differently than we've done in the past. And certainly on connected vehicle, where we're doing a lot of analytics and data. The next three pieces around speed, scale, and fidelity, the outcomes. If we're leveraging the other pieces, what can we get here? And I actually tried to mix it up a little bit. I tried to pull in a little bit from our national laboratories. And I also wanted to let all of you know, under the learn and deliver piece, is we're constantly learning. And I'm encouraging everybody to be a constant learner. Go to these national lab locations and look at the most recent programs and projects that are coming out. And you would first think that, can these apply to something that's physical like automotive? And I'm telling you, they absolutely can. We're looking at them for what is happening in the engineering and science that's getting created? How are the products coming together with what's being looked at from a scientific discovery or engineering? And you will find that you can apply them to your other areas of work. And I used a few examples here. The first one is around just understanding life under the topic of machine learning and AI. It's taking and understanding and breaking down how we build up the fundamental building blocks of what ends up being, unique to us and the building blocks of life and becoming a cell. We're actually doing that now with machine learning and AI, and there are programs and projects around that. And if you look at the fundamentals of the actual technology architecture of how the machine learning and AI is done, it can be applied to other things, like our connected data strategies. Another piece is around chemistry and materials. Chemistry and materials is universal in many areas. If you think of Procter & Gamble, where chemistry and material science is coming together every day in the formulation of what we come in contact with, like a shampoo. But chemistry and materials for engineering and automotive is certainly true as well. It's the chemistry of what these components go through every day from a reliability and durability cycle. It's the materials themselves in being able to design new materials, novel ones. We see the areas of metallic 3D printing now exploding because we have systems and tools that are coming online that are capable of higher volume. We are creating new materials in those spaces. There's new chemistry formulations of the material and actually new metallic materials for the purposes of 3D printing. And then the fidelity around the physics. We always talk about speed and scale and how these are happening on these large-scale machines, but the granularity of the data that we're getting now is unlike anything we've ever seen before. And really it relates to all of the other items above. It's the data, the models that we now have, at the resolution that we're now leveraging with the high-performance computing, and we are seeing insights from the data that we're seeing back visualized, unlike anything that we've ever seen before. So I'm going to stop there and open it up to some questions.
Good. If you could use the microphone there and also introduce yourself for your question.
Sure. My name is Balaji. I'm part of Broadcom. And my question is, does Ford use its internal network infrastructure, HPC infrastructure, to do this modeling, or do you use HPC from any of these labs or GCP or Amazon?
So the question was what type of infrastructure is being used on this high-performance computing. So I'm going to give you my experience from the past and present. At Ford Motor Company, the majority of our modeling and simulation work is done on computing systems that are on-premise. From some of my former work in the past, we did it on both. We did it on-premise, and we used hyperscalers like AWS, as well as Microsoft Azure. And there are others right now that are also using Google Cloud successfully with high-performance computing. And if you have some more questions on it, I'd be happy to answer even on the side.
Hi, Dana O'Connor. So you mentioned the availability of a lot of data. So are you mostly using publicly available data when creating your own models for the private sector, or are you generating your own data, or how does that work?
Great. So the question is around the data. Are we using public data, or are we using mostly I'm going to say we're using mostly our industrial data. And I think for the MLAI piece, I think that's a good thing. But what we're doing with the data now is we're getting much better. When we say big data, it's curated, it's in one spot, it's classified, so that we know and can separate the certain data sets. And when we get into engineering, we are being much more vigilant about how we're managing that data going forward. Our final production releases of those models and the first principle physics models that were used with them are now being aggregated in the same locations. And what we're now doing as a result of that is we're leveraging them as our machine learning libraries going forward. And then as we create something new, we're curating it and putting into those data sets. We're also creating things that we call surrogate models, which are models that are created from machine learning and AI, and we're keeping only the best ones, and we're putting those into our training sets. Susie?
Hi, Susie. Is that on? Yeah, yep. Susie Titchener from Oak Ridge. Dave, what do you see today as the biggest user of high-performance computing? Is it CFD? Is it the classical modeling and simulation that you would use for car crash analysis? Is it AI? What's really soaking up the cycles to the annoyance of everybody else? And what do you see that it will be in 5 years?
Yep. So my easy answer to that one, because I brought the top 3 in here to talk about today. And it's a pretty even distribution between the 3. Between safety crashworthiness, the design of the vehicle around aerodynamics, but taking into account the systems approach, and then the connected vehicle, all that data, those are our top 3 at about a distribution, let's say a third, a third, a third of each. Where do we see that going in the future? That's a great question, because we're trying to understand that with where also machine learning and AI are going. Because let's say just in the engineering design space, it's already becoming very disruptive in a good way on how we're using the compute cycles. So if we use the same distribution, the only thing that I would add right now is that I think that the machine learning AI piece for each one of those, for the first 2, will probably be like an 80-20. So even 80% in the safety and the other space. And when we get to connected vehicle, I would even put the number at like 90 to 100% with some elements, or if not many elements, of machine learning and AI.
Umesh Palia, GE Aerospace. So Dave, you've worn many hats over the last decade plus. So this is asking you to take a step back and think through what lessons have industry, national labs, and universities learned in terms of what could we have done better to accelerate the adoption of HPC, especially as we are in the frontier of starting the whole AI ML. That's kind of the next space where industry is going to start trying to understand what's the return on investment, how much should we invest in it. So are there any learnings from the past 5-10 years where industry, in partnership with national labs and universities, adopted HPC that we should learn, bring it to the AI space?
So a couple parts to your question. The first and important piece is, from those lessons learned, how can we accelerate the adoption of HPC from these great learnings and GPU acceleration and many other pieces. I believe that this conference here already is a huge start to that. The one thing that we could all do better here is, when we leave with the information that we learn, we need to become advocates in this space. This area of advanced computing and methods and understanding the technologies, we definitely go back and we apply it to where we're at, and we use other partnerships with government or other partnerships with other industries, maybe that we're not competing with, to enable and accelerate our space. But I can tell you what I do. I'm also an advocate even outside of Ford. I'm here today at the Supercomputing Conference, not just to talk about the Ford story, talk about the partnerships that we had with the US government and the DOE and ECP. We need to become a better part of the workforce development, and part of that workforce development starts with the advocacy of these capabilities. Going back to your teams and your organizations, from where you are to your leadership, to others that are your partners in your engineering or scientific space, and then helping those that are new to this. I'm already talking to others that are here. There's a mentor protege program here at Supercomputing Conference. Please take part in that. Those are pipelines for our future workforce development that can come into any one of the work streams, whether it's academia or government or industry. I think those are the best ways right now that we can actually not only influence, we can do more than influence. We can make and create actions around that as leaders and others that are in this area. So, great question.
Yeah, Robert Gaboy, machine learning graduate student. You mentioned talking, or you talked about looking at what the national labs are doing and applying it to your industry. Do you publish case studies on how you successfully use that, and where could one find those?
Great question. And I'm going to take that as, does industry publish as well, right? Not just academia and government. Industry is getting better at that. We should take the publications that are coming out of academia and the government, the national labs. But some examples here, both former and other, is that around some of the ML AI technologies that have been leveraging the heterogeneous CPU, GPU systems, there are publications. A forum that is better than I think many other industries at that is actually aerospace. Aerospace actually has industry forums, and when you go into them, like AIAA, when you go into AIAA, you would be amazed at the number of publications across all of the industries and partners that are within aerospace, sharing how they're creating new ML/AI products and how they're leveraging this type of computing that we're talking about here today. So I'm giving you an inroad to say, go into some other industry sectors and you will find that they are publishing. But in some others, we need to do better, especially in, I think, healthcare and transportation, automotive.
Thank you.
Hello? Oh. Dana O'Connor, Pittsburgh Supercomputing Center again. So something that we were promised by industry, famously one person in industry, is that we'd have self-driving cars by now. And we were also promised that, LLMs were going to take everybody's jobs. So I guess my question is, are there other AI trends that you see in industry that that were thought to be true maybe 5 years ago, but maybe aren't necessarily true now? And what do you think is kind of those sorts of trends now that will not be true 5 years from now?
Gotcha. So I heard that question as, we did say that self-driving cars were going to be so pervasive by now that, and then you're relating that to where we're at with the inflection points in computing and machine learning and AI, is that maybe a little bit overhyped, and we're not going to be as far along as we say we're going to be. So the first one I'll talk about, automotive. Still working on it. The electrification and software-defined vehicles, not a surprise, are as complex as we thought they would be. And then there are other key enablers, which is infrastructure. The infrastructure enablers right now are probably one of the longer in the tooth pieces to be able to have more ubiquitous and larger scale self-driving vehicles in a larger scale inner city. There's infrastructure that needs to happen. There's plans and roadmaps around that infrastructure. Meanwhile, the electrification and software of the vehicles is really continuing to go down that path. So I think there are some points in time where it'll start scaling even more. The second piece around machine learning and AI, the only thing I would say to that one in comparison is that there's less roadblocks. There isn't like this massive infrastructure roadblock. And I'm going to relate that infrastructure to big city, big cost. You can do machine learning and AI on very, let's say, low cost, easy to obtain computing systems. It doesn't need to start off on a national laboratory exascale system. You can do machine learning and AI, as many of you know here, in your office or at your home. And so that's why I think it will be different in comparing the two. And the number of people in computer science right now at any university, the machine learning and AI is just infused as part of the curriculum now. And I think when you combine those efforts, there's low barriers to entry, so that's why I think it's going to continue scaling at a very high rate. This is my thought. So,
Good.
great questions.
Yeah.
Questions.
So she was promised self-driving cars. I was promised flying cars when I was a kid,
okay.
so
Yes.
you got to get on that too.
Yes.
So. Good. All right. Well, let's thank Dave, and we will bring him back up for a panel at the end here. So.
I'm sorry about the clicker starting off.
No, that's good.